Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.1, day 1, entitled, What is a Function? And today we're going to talk about the first 3 objectives. We're going to talk about functions and how they are all around us in the real world. We'll define what a function is, and we'll evaluate functions. We'll talk a little bit about domain and range today, but not too much. We'll talk more about that tomorrow. Okay, and functions are all around us. In nearly every physical phenomenon, we observe that one quantity depends on another. Your height depends on your age, the temperature depends on the date, and the cost of mailing a package depends on its weight. So we use that term function to describe that dependence of one quantity on another. So we say the height is a function of age. Temperature is a function of date. The cost of mailing a package is a function of weight. And here are some more examples. The area of a circle is a function of its radius. The number of bacteria in a culture is a function of time. Weight of an astronaut is a function of elevation. The price of a commodity is a function of the demand for that commodity. So we could think of other real-world examples too. This is just a few to get you thinking. And sometimes you have a specific rule that describes a function, and it's called a formula. And here we have the formula for the area of a circle. So the area of a circle depends on, or is a function of, the radius. So we have the formula area equals pi r squared. But even if we don't have a precise rule or a formula that describes the function, we can still describe the function by looking at its graph or making a graph. So they have an example here of when you turn on the water faucet. The temperature of the water depends on how long the water's been running. So if we made a graph of that, the temperature would increase over time. So we would say that the temperature of the water from the faucet is a function of time. Okay, so with that just brief little background of functions, now we come to our actual definition for a function. And they say that a function is a rule. And more specifically, down here in the little box, it says it's a rule that assigns to each element in the first set exactly one element in the second set. So that first set that we start with, that's going to be our domain, and the second set that we end with is going to be our range. And we have specific letters that we use for functions. Usually we use F. So we'll say F is the rule for a specific function. F stands for function. Sometimes F is already taken, so then we go alphabetically. G, H, I, J, K. And usually when we consider a function for which the sets A and B are sets of all real numbers. So any number that we can think of, we could put into a function, unless we have certain restrictions on it, and that's where domain and range come into play. And we're going to see this terminology again, this little notation here, this element. Okay, so that would say that for this function, f, x is an element of the set A. And that function notation, f of x, they describe it right up here. And we read that as f of x. We don't say f times x or f parentheses x. It's written with the x in parentheses, but that tells you what quantity you're putting into the function. So it's not really multiplication, it's a notation form, it's a function notation. And whatever value is in that parentheses after the f that stands for the function, that tells you what you're substituting into the function for the variable. Okay, and when we have our domain values, Those are also referred to as independent variables. So that's any number that we can pick independently and put into the function. And our range values, those are going to be our dependent variables because they depend upon the number that's picked for the domain and the function in order for them to exist. And really how you need to think of a function is kind of like a machine. I like to think of it like a pop machine or a vending machine. And you come up to the machine and you have some kind of input. Usually it's your money. And you input that money into the vending machine. And then you push your buttons. And then the vending machine does its work. And it kind of goes clunk, 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 thump, thump. And then boop, out comes your output. And that could be your Pepsi or your granola bar, whatever kind of machine you're at. So if x is the domain of the function, when x enters the machine, it is accepted as an input, and then the machine produces an output. And this is a good way to help you know if a function actually exists as a function, if a relation is a function. And there's another way to represent it too. You could represent it as pictures with like little bubbles and little arrows. And again, you could think of this as a vending machine or a pop machine. This in set A, this would be your button that you would push for X, and then it would give you an output of f of x. So let's say that's the Pepsi button. So you push the button for Pepsi, you get a Pepsi. Now this little button A goes into the function and you get f of a out. It's the same thing as if you push the button for Diet Pepsi, you get a Diet Pepsi out. Okay? The thing is, we have to remember that you can't have one value that gives you two separate outputs. You can't have one input that gives you two outputs. So you can't push the button for Pepsi and get a Pepsi and get a Diet Pepsi. If that happens, that means that that vending machine isn't stocked properly, and it means that your function's not working properly. So this is a good visual representation that each element in the first set has to match with exactly one element in the second set. Each input has to have exactly one output. Now you could have a vending machine that all gave you the same thing. So you could have a whole bunch of different buttons, and when you put them in, you put your money in and you push the button, they all give you the same thing. That can happen. That's like 3 people having the same birthday. That can happen. So either of these cases are acceptable functions. The one that's not acceptable would be if you had 2 values that gave you the same output. So if you substituted in 1 and it gave you 7, and then you substituted in 2 to the function and you got 7, that couldn't happen. You can't put 1 into an equation and get 7 out, and then put 2 in and get 7 out as well, unless you also put 3 in and it gives you 7. If you have this type of a relationship, then that's okay. You cannot have this. So this is not a function. So for example 1, we're just going to talk about some generalness of our function here. We have a function f of x equals x squared plus 4. There's our function. And part A says to express this in words. So basically what this function is doing is it's taking the input and it's squaring it and it's adding 4. So we could say that it squares the input or the input value, and then it adds 4. So that is what you would have to do. If they gave you a value for x, you would square it and then add 4 every single time. So now for part B, they're going to give you some values. So they give you f of 3. So that means they want you to substitute 3 into that function where the x is. So we'll have 3 squared plus 4. So that's 9 plus 4, which is 13. And it works the same with negative numbers, f of negative 2. Remember though, if you're squaring a negative number, the negative goes with the number when you square it. So negative 2 squared plus 4, that's going to be 4 plus 4, which is 8. And for this third one here, we have the square root of 5, so we're going to substitute that into the function. So the square root of 5 squared plus 4. So the square root of 5 squared is 5, plus 4 is 9. So again, any real number that you put into the function will get you a value out. So even a radical is going to be a real number that you could substitute into the function. So that leads us into part C on the next slide. Part C says to find the domain and the range. And like I just said, we can put any number into that function. So our domain is going to be all real numbers. However, our range is going to have a slight limitation to it. And remember, our function was x squared plus 4. And if I was to graph that, I would get a parabola. And it would have symmetry around the y-axis. But its intercept would be at 4. So that's a really rough graph of what our parabola would look like if I graphed that function. So notice that I could put any number, any positive or negative x value in, but my y values never go below 4. So my range is going to be all of the y values greater than or equal to 4. You can write it like that, or you can write it in set notation. And the reason that happens is because when you square the function, or when you square the input value in the function, that x squared value, whatever number you put in for x, positive or negative, it's always going to be a number that's greater than or equal to 0. If you put in a negative number and square it, you get a positive number. If you put a positive number in and square it, you get a positive number. So you're always going to have some positive number plus 4 that you add to it. So you're always going to end up with a situation where you have x squared plus 4 is greater than or equal to 4. So this is the value that you have to stay at or above for this particular function. And then they want us to draw a machine for this function. And you can draw that however you'd like. If you want to draw it like the little box that we saw in the first picture, or if you want to draw it with the little bubbles and the arrows, that's fine. But you're taking your x value, which is going to be your input, and you're putting it into the function. And that function is the x squared plus 4. You could write it with symbols like that, or you could write squared plus 4. Like we wrote it in words for part A, square the value and then add 4. And then your output is going to be whatever that is, the x squared plus 4. And remember, sometimes I'll write that f of x. So that's your value that you get out after you've put f into the function. Okay, now when we evaluate a function, we've already kind of evaluated a function in part B there. But just remember that when we're doing this, we have our independent variable that we put into the function. And you kind of want to think of that like a placeholder. Don't think of it like multiplication. And if we have this function here, f of x equals 3x squared plus x minus 5, that x is our input value, and it's really like a little placeholder. So this diagram that they have here is a really good visual representation. It's just a spot that you're filling. So if they tell you to find f of 5, then you would put 5 in that spot where the x's are. And then you just do order of operations to evaluate it. Okay, so our last example for today then is just to practice evaluating these functions again. So we have 3x squared plus x minus 5 for our function. So when I see this notation, f of negative 2, that means I'm going to substitute a negative 2 into my equation wherever I see that x is a variable in this case. So this will be 3 times 4 minus 2 minus 5, and 3 times 4 is 12. So 12 minus 2 minus 5, that's like 12 minus 7, so that's going to end up being 5 altogether. F of 0, that should be very straightforward to plug 0 into this function, or substitute 0 into the function. Anything times 0 is just 0, plus 0 minus 5, that's going to get us negative 5. F of 4 means we're going to substitute 4 into the function. So this will be 3 times 16 plus 4 minus 5. So 3 times 16, that's 48, plus 4 and minus 5 would get us a grand total of 47. And you can even do this with a fraction, f of a half. So I'll have 3 times 1/2 squared plus a half minus 5. So 1/2 squared is 1/4. So that would be 3/4 plus a half minus 5. And if you're a little shaky on doing the mental math with the fractions, you could convert it to decimals or use your calculator. You'll get negative 15 over 4 as a fraction, or as a decimal, you get negative 3.75. And you can leave your answer as an improper fraction. If you wanted to write it negative 3 3/4 as a mixed number, you could. Just make sure if you leave your answer as an improper fraction that it's reduced down all the way. Okay, so there is your practice set of problems to practice these concepts. And if you have any questions, come on in and see me before school.